Hey folks, welcome back. In this video we're going to kick off the subtopic of interference by looking at phase and coherence. So let's get started. We're now on to the waves part of the particles and waves topic where we look at interference. And the first thing we're going to look at is phase and coherence, and these are two new terms which you've probably not heard of before. So first of all, it says interference patterns can be observed when coherent waves overlap. So if we take two separate waves and we overlap them, then we can produce something called an interference pattern. But these waves must be coherent, and waves are said to be coherent if they have the same frequency, wavelength and speed. So if you think about the wave equation V equals F lambda, the two waves must have the same F, i.e. frequency, the same lambda, i.e. wavelength, and the same V, i.e. the speed. So all terms of the wave equation must be the same for the waves that are overlapping if you want an interference pattern produced. It then says if two waves are emitted from the same source, it is likely that they will have the same frequency, wavelength and speed, and will therefore be coherent. This cannot be said for two waves emitted from different sources, however. So as an example, if you had two loudspeakers connected to the same signal generator, then because the signal generator is set to a particular frequency, that means both of these speakers will have the same frequency. So that means the waves produced from the loudspeakers will be of the same frequency and the same speed and the same wavelength, since they're both connected to the same source. And we would therefore detect an interference pattern when the sound waves from these two speakers overlap. However, if we were to remove one of these speakers, let's say we got rid of speaker 2, and there was only one loudspeaker connected to the signal generator, then we wouldn't observe or be able to hear an interference pattern from speaker 1, because there's no other waves to interfere with the waves from loudspeaker 1. And I'll just show you a quick simulation to help you visualize this. So here we've got a sound generator and a double slit, and let's say this double slit was representing our two loudspeakers connected to the same signal generator. So if we had our waves produced from these two separate loudspeakers, we could say that these waves are going to be coherent, and when they overlap, they're going to produce an interference pattern which looks like this. So you'll hopefully notice we get these dark regions here, here, and then these ones down the bottom and the top going off the screen. And these are what we call points of destructive interference, and you actually get points called constructive interference in between these. So directly in the middle here we get a point of constructive interference, in the middle here, in the middle here, and so on. And the reason I'm showing you this is because if we were to get rid of the two slits and make it just one slit, then you'll notice with just one sound source or one loudspeaker, we just get this sort of diffraction pattern produced, where the waves are bending through the gap here. And that means there's no interference pattern produced here. So if you remove one of your sources of sound waves in this example, then you no longer get an interference pattern. And it works the same for things like light waves and water waves and so on. Jumping back to the notes now, it says when two waves are overlapping, the term phase can be used to describe how in tune they are. Two waves are said to be completely in phase when the crest of one matches up with the crest of the other, or the trough of one matches up with the trough of the other. So at this point it's a good idea to recap the parts of the waves. So remember, the crest is the top point of a wave, the trough is the bottom point of the wave, the amplitude is half the vertical height of the wave measured from the axis up to the crest or the axis down to the trough, and the wavelength is defined as the horizontal distance of one full wave, which can go from trough to trough as shown here, which is the same as the horizontal distance from crest to crest, or the horizontal distance from one point on a wave to the same point on the next wave. So going back to the notes, we're saying that two waves are said to be completely in phase when the crests align and when the troughs align. So you've got crest meets crest and trough meets trough. And then it says that two waves are said to be completely out of phase when the crest of one matches up with the trough of the other. So here we've got the top point of the wave matching up with the bottom point of the other wave. And that means that as you go along, you've got crest meets trough, and so on. So we can say that two waves are completely in phase when the crest meets crest or trough meets trough, but we have that two waves are completely out of phase when the crest of one meets the trough of the other. It then goes on to say the coherence of waves can also be defined in terms of the phase difference between them. So this is talking about the difference in how in tune they are. So it says two waves are coherent if they have a constant phase relationship. And this is a very important phrase to try and remember for the exam. So if you're asked what is meant by two waves being coherent, then you need to state that it means they have a constant phase relationship between them. And you could also say it means they have the same speed, frequency and wavelength. But this is the main phrase that you want to state, constant phase relationship, and you'll find this in the learning outcomes from the SQA. It then goes on to say that this phase difference or phase relationship can be zero, as in two waves that are in phase, or non-zero, as long as the relationship for the phase stays the same. So what we're saying is, because the speed, frequency and wavelength are staying the same, we don't want one wave to be able to speed up to catch the other one, for example. The difference between them must stay the same, and that's what we mean by the constant phase relationship. So if two waves are exactly in phase, then we say the phase difference between them is 0. But if two waves are not exactly in phase, then we would say they have a non-zero phase difference. There is some phase difference. But we just want that difference to be constant for coherent waves. Moving on, we're going to look at the two main types of interference, which are going to underpin most of what we look at in this interference topic. So the first one is constructive interference. And it says that when two waves of equal amplitude meet in phase, i.e. the crest of one meets the crest of another, or the trough of one meets the trough of another, they combine to form a wave of twice the amplitude. This is called constructive interference. The two individual waves add together to give a wave of higher energy, as shown below. So it's a wave of higher amplitude as well. So here, if we had two waves overlapping that were exactly in phase, we would end up with a wave that has twice the amplitude and therefore a higher energy. However, the second type of interference is the opposite of this. It's called destructive interference. And it says that when two waves of equal amplitude meet out of phase this time, i.e. the crest of one wave meets the trough of the other, they combine to form a wave of zero amplitude. This is called destructive interference. The two individual waves cancel out to give a wave of zero energy, as shown below. So here we've got the crest meets trough, trough meets crest meets trough, and so on. And if we combine these two waves that are completely out of phase, then we end up with a wave of zero amplitude and zero energy. And this line is just showing you that there's a wave of zero disturbance produced. And lastly, it says to note that if the waves are not of equal amplitude, then complete cancelling out does not occur. Now, just as a wee aside, you might have come across destructive interference in everyday life if you've heard of things like noise cancellation before. So for example, you can buy headphones such as these Bose headphones that have noise cancellation built in, and the way the noise cancellation in these headphones work is that they have a microphone built in that listens to the surrounding sound in the room, so it's taking in sound waves. And the clever part about the headphones themselves is that they send out sound waves within the headphones, the parts that I can hear, which are opposite to the sound waves that are being picked up from around the room. And the idea is that the two waves will cancel out just like the waves here. So the sound waves from the background noise will be cancelled out by the sound waves that are emitted into the headphones here. And the result is that you get this cancellation of the background noise. So if you've not tried noise cancelling headphones or earphones before, I'd strongly recommend it because they do work very well in cancelling out low frequency sounds such as hums on public transport like trains and aeroplanes and so on. Now I'm just going to show you a few simulations to help you visualize constructive and destructive interference. So firstly, let's say we have two slits here called a double slit, and we have waves, and this could be light waves, water waves, sound waves, or microwaves, for example. So let's say these waves are what we call wavefronts. They are straight line waves, and if we click play here, you'll see that they pass through the double slits, and you'll see they start overlapping as well. Now, when they overlap, we get what is called constructive and destructive interference patterns. Now, the points of constructive interference are always found directly in the middle, and then at alternate regions as you move outwards from the middle. So we have constructive interference in the middle where the two waves overlap. Then we have a point of destructive interference here, where we get crest meets trough. And then after this, we get another point of constructive interference, and then we get another point of destructive interference. And it works in this kind of alternate way. So next to a point of constructive interference, you would get a point of destructive interference, and so on. And if you move down the way from the point of constructive interference here, you get again the point where crest meets trough, so you get destructive interference here. And then you get back to crest meets crest or trough meets trough, where you get another point of constructive interference, and so on. So just to label those points for you, here we have these purple lines representing the points of constructive interference, where we get crest meets crest or trough meets trough. And then these green lines show the points of destructive interference, where we get crest meets trough. Now I'll just show you this other simulation, which again shows two coherent waves overlapping. So if we have zero phase difference between the two waves, that is, they are completely in phase, then the two waves will overlap to show a point of constructive interference over here. So we've got crest meets crest and trough meets trough. Whereas if the two waves don't have zero phase difference in between them, we can get a point called destructive interference. So because the waves from this slit are travelling further to get to this point than the waves travelling from this slit, then it means that the two waves are meeting sort of half a cycle out of phase. You've got the crest of one wave meeting the trough of the other, and that means that these waves are producing a point of destructive interference. We could keep going though and get to another point of constructive interference, such as up here, where we're saying that even though the waves from this lower slit are travelling further up to this point than the waves from the upper slit, we can still get the two waves meeting completely in phase. So we have crest meets crest and trough meets trough up at this point. That's all for this video, folks. I hope you found it useful. If you did, give it one of these, subscribe to the channel, and I'll see you in the next one. Take care.